Just want to make a quick video this morning over what we're going to be covering the next couple days. We're going to be talking about pedigrees. So pedigrees are a chart, like it says here, a chart to help trace the phenotypes, and sometimes we look at the genotypes in a family to determine whether members carry recessive alleles, or to trace, we kind of want to trace a certain, maybe a disorder or a certain characteristic or a certain trait through the family, and we'll use this pedigree chart to do that. And a little bit about them. Before we get into the pedigree, last week you did your research over a recessive disorder or some type of genetic disorder. Some of you chose recessive ones. I think a couple people chose dominant ones, but more often than not, those disorders are going to be recessive. They're more common because recessive disorders aren't going to go away, because you'll always have the opportunity or the possibility of having parents that are carriers of the disorder, and they're perfectly healthy, but they can pass that on to their children. Some examples here: cystic fibrosis is probably the most common of the genetic disorders, the recessive ones. It's most prevalent. It's whenever you have a lot of the mucus in your lungs, you can't break it down, and it starts to build up, and people with cystic fibrosis tend to suffer a lot from pneumonia. I think the life expectancy, maybe reach around 30. They have to get a lot of treatment throughout their life, through medication, through actual physical breaking up of the mucus in their lungs. Sickle cell anemia is another one that is pretty interesting. So sickle cell anemia is whenever your red blood cells are not that little round donut shape, but they're this sickle shape, and so they don't carry oxygen very well, and they get hung up in your blood vessels. And people with sickle cell anemia have a lot of difficulty. They have low oxygen levels, have fatigue all the time, and can suffer other problems from that. They usually have to get blood transfusions on a fairly regular basis to get those good, healthy red blood cells in their body. A little interesting fact we talked about yesterday in class about sickle cell anemia is this concept called the heterozygote advantage. So if you have sickle cell anemia, your genotype is a. You're homozygous recessive. In some third world countries where malaria is a problem, of course malaria is a disease transmitted by mosquitoes. If you are big A for sickle cell anemia, means you don't have sickle cell anemia, you're homozygous dominant, but you're prone to get malaria. But however, if you are heterozygote, if you are big A, you do not have sickle cell anemia, and you're actually immune to malaria. So it's actually advantageous to be heterozygous for this particular trait. So most of the population in these areas are heterozygous because they survive longer. And because a lot of third world countries and a lot of countries in Africa have to deal with this problem of malaria, and they have the sickle cell disease, that has transmitted over into America. And so if you look at the American population, among the American population, typically African Americans have a higher rate of sickle cell anemia, just because that came with them in their heritage when they came over from Africa. It can happen in any race, but it is more prevalent in African Americans. And then Tay-Sachs disease was one you watched the video on where it's a recessive disorder. It's pretty rare, but you have to have two parents that have to be carrying that recessive trait, pass it on to their child. Now, there are others, and you guys researched some others out there. One of the dominant ones I wanted to talk about is Huntington's disease. Most dominant disorders they're not around because you think about it, you either have it or you don't. So if you have it, odds are you're not going to survive long enough to grow and to have children of your own, so you won't have as likely a chance to pass it on. Most of the time they would probably die when they were younger from a dominant disorder. But Huntington's disease is a rare example in that the symptoms of Huntington's disease doesn't typically show until your late 30s, maybe early 40s. And by that time of your life, you've possibly already had children. And if you have Huntington's disease, again, it's not very common. You're probably a big A, little a genotype for it. but because you have that big A, you have it, and there's a 50% chance you're going to pass that on to your child. So you're either going to give them that bad dominant gene or the recessive gene that's harmless. But so there's a 50-50 chance. A little bit about it. It's a disease that affects your nervous system, and you start to you have shakes. Their nervous system starts to deteriorate. They look a lot older than they actually are, real thin, unhealthy. Typically don't survive probably maybe to 50, a little or beyond, maybe to 60, but most of them probably die before then. So that's Huntington's disease. Now, we'll talk about pedigrees real quick. When you're dealing with a pedigree, circles are females, squares are males. When you have a horizontal line, that's to indicate a marriage or a mates, and then the vertical line is going to be children. So this is what they look like. So you have this woman and this man have these 3 children, 2 boys and a girl. This boy married this girl, and they had 2 daughters. And then this daughter married this man, and then they had 4 children, 3 boys and 1 girl. So when they're shaded in, that indicates that they have this disorder, or they have the trait that you're tracking. Now, when you're looking at this, what you would want to be able to do with pedigrees is look at these oftentimes and determine what the genotypes of the individuals, the ones that you can. So if we wanted to determine the genotypes of these individuals, we could look at so if they're shaded in, first of all, I know that this is the first thing I want to do is determine, is this dominant or recessive? I know that this is recessive because I can look and see these 2 individuals have it and their parents don't. So that tells me that both these parents have to be big A, little a. All right, both of these here are big A, little a. And so anything that's shaded in, any of these individuals that are shaded in have to be little a, little a. Okay, sorry I'm trying to do this with my mouse. And we can go up here and look at this individual as little a, little a. Now, with this one individual being homozygous recessive, if this one were heterozygous, odds are out of the 3 children, one of them would probably have it, because there's a 50% chance that they would have it. So we know that it has a big A. I'm going to assume in this case that it is homozygous dominant. So if that's the case, every one of these children here are going to be heterozygous because they got a big A from their dad, and they got a little a, oops, sorry, that should be a big A, and a little a from their mom. Now, the other thing I forgot to mention, when you're looking at these, you want to determine if it's autosomal or recessive. So hopefully when you did your research, you realized that autosomal means that it is on one of your regular chromosomes that has just your 1 through 44 that don't have anything to do with your sex. Those are ones that have eye color, hair color, how tall you are, things like that, enzymes that are inside your body. But the 2 chromosomes that are sex-linked are those traits that are on your sex chromosome. So typically they're on the X chromosome. And they have to do, and there are some disorders that are that way. Hemophilia is one that is a sex-linked trait. Some color blindness is sex-linked, and those traits are on the X chromosome. Now, how you can tell if a pedigree is, if we're looking at this disorder, how do you tell if it's sex-linked or autosomal? Remember, typically males get sex-linked traits way more frequently than females because they only have to get 1 bad X, where the females have to get 2. So it's easier for the males to pick up a sex-linked trait. So in this case, on this pedigree, you'll notice there's 2 females that have it and 1 male. That tells me right off the bat this has to be autosomal. Now, if only males were shaded in, that would be a big clue that it is sex-linked. So this individual here, I'm going to look at it, and I really don't know what its other letter is because when we can look, yeah, it has 2 children that don't have it. Odds are it's probably big A, but it could be big A, little a. 2 children's not enough, so you might draw like a big A dash. Now, this individual here, we talked about that. Now, this child, we know it has a big A. The other A, we really don't know for sure because it doesn't have any children of its own, so I would probably give it a big A dash. Now, these 2 boys here, we know they have a big A because they don't have the disorder. And again, they could have received a little a from one of their parents, or they could have received a big A. But until they have children of their own, I'm going to give them a big A dash because I really don't know what that other letter is. So that's a little bit about pedigrees. Today I'm going to post an assignment where you will go through, and a lot of these will take you baby steps in learning. One thing I forgot to mention, almost forgot. When we have to number pedigrees oftentimes. So we label each generation with a Roman numeral. So this would be generation Roman number 1. This is 2. This one is 3. And this one would be 4. And then we just give it regular numbers from left to right. So this would be 1, and this would be 2, and then this one would be 1, 2, and 3, and 4. And then we'd start off and go with 1, 2, 3, and 1, 2, 3, 4. So how we recognize certain individuals is by this numbering system. So if I want to talk about the individuals in this population that have the disorder, I would say it's individual 1-1, individual 4-1, and individual 4 IV dash, what's that, 3. So that's 1-1, this is 4-1, and this is 4-3. So that's the numbering system when we're dealing with pedigrees. Some of the pedigrees that I gave you today will actually won't be numbered like this. They're actually numbered like 1, 2, 3, 4, 5, 6, 7, 8, and so forth. That's okay. Just if they're not numbered, you want to go with this plan. And but if they have already numbered, then just go with how they have numbered it. So if you have any questions about pedigrees, feel free to shoot me an email. And hopefully this will make some sense, and you'll have fun. I think they're kind of fun. It's kind of sometimes like solving a puzzle, and they can be challenging. But let me know if you have any issues. Talk to you later.